Now let's move on to the transpose of matrices. First thing, we're going to look at the size requirement. For requirements of size, there is no requirement for the size to make any transpose. So you can always have a transpose to any matrix that you might have of any dimension. Okay, so there is no requirement for sizes of matrices to make a transpose. Let's take some examples here. Example number 9, if A is a 1 by 3 matrix, you can transpose it and the results will be a 3 by 1 matrix or vector. Example number 10, for B, if it's a 3 by 2 matrix, you can transpose it and the results will be a 2 by 3 matrix, which is the exact opposite of the dimensions of the original matrix. Example number 11, if C is a 3 by 5 matrix, the transpose would be a 5 by 3 matrix. Example number 12, for D matrix, if the matrix is a 3 by 3 matrix, it can be transposed to a 3 by 3 matrix as well. How do we do the transpose? Let's see here. If we have a transpose, we can take every row and make it into a column, or we can take every column and make it into a row. Okay? So let's see here for a general example. If I have K, an n by m matrix that you see right here, then if I want to transpose K, the symbol for this is K, and then above the K on the right, I put T, which is a transpose. And that would be, I'm taking each row now and put it into a column. So I'm going to take the first row and make it into a column. Okay, you can see these are the same elements. And then the second row, I make it into a second column. And then all the way down to the last row, which will be last column. Okay, and of course the dimension, instead of n by m, they become m by n. Let's take solutions for the examples that we had presented earlier. So example number 9, if A is a 1 by 3 as a row, then A transpose will be a 3 by 1, and we take the same row and make it into a column. Example number 10, if B is a 3 by 2 matrix, B transpose would be a 2 by 3 matrix. And we're going to take every row, like first row would be first column, second row would be second column, third row would be third column. The other way also, we can do first column here, make it to first row, and second column, make it into second row. Either way, you'll get the same results. Example 11, if I have C matrix, which is a 3 by 5, I can transpose this matrix to become a 5 by 3. So I'm going to take each row here, make it into a column. So row 1 goes to column 1, row 2 becomes column 2, and row 3 becomes column 3. You can do the same thing if you want to do it the other way. You take the first column here, make it row 1, and then second column, make it row 2, and so forth to the end. Example number 12, if I have D of a 3 by 3 dimensions, and I'd like to get the transpose for this, it will also be 3 by 3. Again, I take the first row, make it to first column, and then second row to second column, and third row to third column. Another important operation that I want to talk about is the matrix inversion. So getting an inverse of a matrix. Let's first look at the size requirement for matrix inversion. For a matrix inversion to be possible, the matrix must be a square matrix that is full rank. So it has to be a square matrix and full rank. The number of columns must be equal to the number of rows, which makes it, of course, a square matrix. And for this particular course, we're going to focus only on inverting a 2 by 2 matrix and a 3 by 3 matrix. Okay. Of course, more higher order matrices can also be inverted. It can be more complicated and it gets really difficult and lengthy as the number of rows and columns increase. Okay, so let's take a couple of examples on the size requirement. So if I have matrix A, for example 13, and matrix A is a 2 by 2 matrix, square matrix, the resulting inverted matrix would be a 2 by 2 as well. Example number 14, if I have a B matrix, which is a 3 by 3 matrix, the resulting inverted matrix would be a 3 by 3 as well. Now, once we see that the requirements for the size are met, and we determine that the matrix is invertible, then we can go ahead and start with the process of inverting a matrix. In general, to calculate the inverse of a matrix, we need to divide the adjugate of the matrix by the determinant of the matrix. And we're going to talk about each one of these in this review. So let's start with the 2 by 2 matrices. To find the determinant of a 2 by 2 matrix, multiply the two diagonal elements and then deduct from that the multiple of the two off-diagonal elements. Okay, so you multiply the two diagonal elements minus the multiplication of the two off-diagonal elements. To find the adjugate of a 2 by 2 matrix, switch the two diagonal elements. Okay, just switch them, and then change the sign of the two off-diagonal elements. All right, so let's take an example on this. If I have example 13, where A equals to 2, 3, and 4, 5, which is a 2 by 2 matrix. Okay, now to find the determinant first, you can see it here. The determinant is this element times this element, that's 2 times 5, okay, minus 3 times 4. Okay, so I put here that A inverse equals to this is the adjugate of A and this is the determinant of A. So for the adjugate of A, what I did is I switched the two diagonal elements. So here they were 2 and 5. I put here 5 and 2. And then I switched the sign of the two off diagonal elements. It was 3 and 4. Now it's -3 and -4. All right. So I move it into here, and then I found the determinant of the matrix of the denominator. So 2 times 5 minus 3 times 4. Okay? If you do this calculation, you're going to come up with this matrix, which is again 2 by 2, and it represents the inverse of a 2 by 2 matrix. Now moving on to the case when we have a 3 by 3 matrices. Again, we're going to see how we can find the determinant of a 3 by 3 matrix and the adjugate of a 3 by 3 matrix. So let's start with the determinant of a 3 by 3 matrix. If I want to find the determinant of 3 by 3 matrix, let's suppose, for example, we have a general case here where K equals to this 3 by 3 matrix, K11 all the way to K33. Okay, so what I need to do first step here is copy all 9 elements and place them right next to the matrix that you would like to find the determinant for, in this fashion here. So I took all these 9 elements, okay, I placed them here, and then I copied them again and I placed them next to the original elements. Okay, so these 9 elements are a copy of the 9 elements next to them. All right, once we have this, then we can start the procedure for finding the determinant. So I'm going to put here what the determinant of K is, D and then underscore K. The first thing we need to do is we need to find the multiplication of the first diagonal elements. Okay, so, and that would be a positive sign. So I'm going to be multiplying K11 times K22 times K33. And that would be a positive. So I put it right here. Okay. Then I will take the second diagonal elements. So K12 times K23 times K31. And that would also be positive. So plus these multiplication of these elements. And then I'll take the third diagonal elements here. So K13 times K21 times K32. So I multiply these and they have a positive sign, which I put in here. Now I'm going to move to the other direction. I'm going to take the first off diagonal elements of this. I'm going to multiply them, and that will be negative sign. So it will be K11 times K23 times K32. And with a negative sign, that would be negative this multiplication. And then I'll move on to the second off diagonal elements. Again, I multiply these and we'll have a negative sign beforehand. So that's K12 times K21 times K33 with a negative sign. They come here. Okay. And then for the third off diagonal elements, again, I can multiply K13 times K22 times K31, and they will have a negative sign, which I will put in here. Okay, so that would be the determinant of K for a 3 by 3 matrix. Once we're done finding the determinant of the matrix, the 3 by 3 matrix, I put it aside. And now we're going to look at how to find the adjugate of the matrix. So to find the adjugate of a 3 by 3 matrix, we need first to find the cofactor of K. So cofactor is again a 3 by 3 matrix, and this cofactor matrix is needed for finding the adjugate of the matrix. So let's find out how we can determine the cofactor of a matrix. I'm going to call it C sub K. Okay, I'm going to open here a matrix square bracket, and each one of these elements is a determinant of a submatrix from the original matrix. Okay, each one of these. The one that has positive, that means it will be positive whenever we find the determinant, and the ones that with a negative, that means this element will be placed a negative. So for the first row, first column, what I will do, I'll take the original matrix and I'll eliminate everything in the same row and column as the first row, first column element. So this is my first row and first column element of the original matrix. I'm going to delete this and delete every single element of the same row and the same column. Okay, what's left are 4 elements which make a 2 by 2 matrix, and I need to find the determinant of these elements. Determinant, of course, is the multiplication of the diagonal elements minus the multiplication of the off-diagonal elements. Okay, and that would make one element with a sign of plus. Now for the second element, I'm going to go to the original matrix. I'm going to go to the second element, first row. Okay, I'm going to remove all the elements from that row and all the elements from that column. Okay, and the 4 elements that are left, I'll put them together as a 2 by 2 matrix and find the determinant of that 2 by 2 matrix. And the sign for this determinant will be multiplied by -1 for this particular element. Okay, and that will be placed appropriately for the cofactor matrix. Now for the third element here, again I do the same thing. This is the third row, first row, third column. So I go to the third row, the first row, third column of my original matrix, and I remove everything in that row and everything in that column. And what's left here, I can put it together as a 2 by 2 and find the determinant of the 2 by 2 and then multiply it by +1 and place it here. Okay, I can do the same thing again for the second row. I go to the second row of the original matrix. I eliminate all the elements of the same row and same column, and then the 4 elements that are left make a 2 by 2 matrix that I can get the determinant for, and then the determinant will be multiplied by -1. So I keep doing this for all these elements until I reach the end, and once I reach the end, then I'll have all these elements for the cofactor as shown here. So this is positive determinant of this. Of course, whenever we have these 2 straight lines that are not brackets, they are a symbol for determinant. So determinant of these elements, determinant of these elements with a negative sign, and so forth. And that would make my cofactor matrix of K. Now, once we find the cofactor of K, we are ready to find the adjugate of K, which is basically the transpose of the cofactor of A. So adjugate of K equals to the transpose of the cofactor of K. So we already found the cofactor in the previous step. All we have to do is transpose this, and if we transpose it, we're going to come up with this matrix right here. Okay, so from this matrix, we're ready to just find the determinants of all these elements. So I can find the determinants and place them here, and that will give me the adjugate of this matrix. Okay, now once I have the adjugate of the matrix and the determinant of the matrix, then I can divide the adjugate of the matrix by the determinant of the matrix to get the inverse of the matrix. So we now are ready to find the inverse of the matrix as follows. I'm going to put the adjugate of the matrix here that we found earlier. It's a 3 by 3 matrix. And I'm going to divide this by the determinant of the matrix that we found in the first step. Okay, so adjugate of k divided by determinant of k. And that would give me k inverse. Okay, so this is the determinant of the matrix k. And for the adjugate, we have to find the determinant of all these submatrices that we found earlier. So these are 2 by 2, so determinant is quite easy. And that would finally give me the inverse of the matrix K. Of course, I noted here that this symbol, we talked about this symbol here with these two lines indicate that this is the determinant of the matrix in these elements. And that determinant will be the multiplication of the diagonal elements minus the multiplication of the off-diagonal elements. Okay, so we find this and place it here, and then we do the same thing for the second determinant, and so forth until we get to the final matrix. Now let's take an example on how to invert a matrix. So we need to find the inverse of matrix B. This is from example 14 that we mentioned earlier. So matrix B here is a 3 by 3 matrix, and I need to find the inverse of this matrix. So I'm going to place the steps here, the general steps. The first step is I need to construct the equation for finding the inverse. So B inverse equals to the adjugate of matrix B divided by the determinant of matrix B. Okay, and the adjugate of matrix B is the transpose of the cofactor matrix of B. Okay, so what you see here inside without the transpose is the cofactor matrix. Once I transpose the cofactor matrix, then I have the conjugate, the adjugate of the matrix. Okay, and then I divide this by the determinant of the matrix, and that would be my inverse. Okay, so the determinant is already we already found it here, and we have the steps of how to find it that we mentioned earlier. For the cofactor matrix, all these are determinants of submatrices from the original matrix. I'm just going to show you how we found maybe a couple of them. Let's take, for example, the first submatrix here. So if we want to look at this is located on the first row, first column, right? So let me go here, first row and first column. This is first row, first column. So I take this whole row and whole column off, and what's left are these 4 elements, and I can take these 4 elements and place them right here and find the determinant for them. Okay, so that's this. Let me show you how we got another element. Maybe I can take this one here. Okay, so this is placed on the third row, second column, third row, second column. So I come here to the third row and second column. Okay, so I take all the elements on this third row and second column and I take them off. And what's left are 2 and 4 and 12 and 17. So that's 2 and 4, 12 and 17. I find the determinant of these elements and multiply by -1 as per the formula that we found in the previous slide. Okay, so once I find these will be the contents of the cofactor matrix. Once I transpose it, then I got the adjugate matrix, and then I divide by the determinant, which is a scalar, and that would give me the inverse of B. Now, if I evaluate this determinant, I'll find out that it equals -2. Okay, so basically I multiply now this matrix by -1/2. Now, if I evaluate all these determinants for the submatrices, I'll find out that they are of these values here. Okay, so these are the values of the determinants of these submatrices. And then if I divide them by -2, which is the determinant, then I find the final inverse of matrix B. So please try to practice this at home and try to learn how to do it manually. So this way you can be ready for the course. Now let's talk about trigonometric identities that are useful for this course. We're going to cover a few of them in this slide. First, let's talk about periodic identities. If we have sine theta, sometimes we write it as s theta, and that's the same as negative sine negative theta, and it's the same as negative cosine of theta plus 90 degrees, which is the same as cosine of theta minus 90 degrees. Okay, so all these are equivalent to each other. For cosine theta, we sometimes write it as c theta, which is the same as cosine negative theta, which is also the same as sine of theta plus 90 degrees, which is the same as negative sine of theta minus 90 degrees. Okay, so all these are equivalent in here. Now the sum or difference of angles, let's start here with sine theta 1 plus theta 2. We symbolically write it in this course as S12, which stands for sine theta 1 plus theta 2. Please do not confuse this with sine theta 1 plus sine theta 2. That's a different equation. This is sine theta 1 plus theta 2 within the same bracket. And that equals to cosine 1 sine 2 plus sine 1 cosine 2. Okay, so when we see C1, that means it's cosine theta 1, and S2 means sine of theta 2. Okay, now for the cosine, if we have cosine with two added angles, theta 1 plus theta 2, symbolically sometimes we write it C12, and that equals to C1 C2 minus S1 S2. If we have sine of theta 1 minus theta 2, we don't have it symbolically written in any way, but it equals to sine 1 cosine 2 minus C1 S2. If we have cosine of theta 1 minus theta 2, again we do not have this symbolically written, but it equals to C1 C2 plus S1 S2. Now let's look at the sum of squares. Cosine square of theta plus sine square of theta equals to 1. And then the law of cosines in a triangle with A, B, C sides. So the length of the sides is A and B and C. And then the angle opposite to side A is theta. Okay. In this case, we can say that A square equals to B square plus C square minus 2BC times cosine theta. The tangent to the half angle substitution. If we have u equals to tan of theta over 2, then sine of theta equals to 2u divided by 1 plus u squared, and cosine of theta equals to 1 minus u squared divided by 1 plus u squared. Okay, so some of these identities are quite useful in this course, and it's good to have these as reference. So whenever you need them, you can come back to them as we go through the course.